Hello and welcome. In this lesson, we will talk about direct variation and partial variation in relations. In everyday life, we describe a relation as a way in which two or more concepts, objects, or people are related to each other by using the relevance between them. And I would like us to focus on the word relevance here, because this is where the meaning of the word relations stems from. We say that if there is relevance between two concepts, it means that the two concepts are related to each other. Or in other words, we say that the two concepts or objects or people form a relation. And I started off with describing the meaning of the word relation in everyday life because, as a matter of fact, in mathematics, the word relation has a similar meaning. Now, since mathematics deals mostly with problem solving, where we have to find unknowns, we need to know the relationship between the unknowns. So, by knowing one of them, we can discover or figure out a way to evaluate the other. So, the unknowns are most commonly described by the word variable. So, in mathematics, we say that a relation is any connection between two variables. Such relations can be described using different methods. We can use words, or table of values, or a graph, or an equation, or a set of ordered pairs. So, what does a relation described by using words look like? Just like the word problems that you solve normally in mathematics. For example, when we say Anna is 5 years older than Emma, that is a relationship that we are describing between Anna's age and Emma's age. A relation can be described by using a table of values, and we have seen them before because we used them to graph the equation of a line just recently. So in the table of values, remember that we always place the independent variable in the first column and the dependent variable in the second column. And these values of independent and dependent variables will show us the connection between them. For example, I see that when n equals 1, p equals 8. When n equals 2, p equals 5. So when n increases by 1, p decreases by 3. Next, when n increases by 1, so it becomes 3, p decreases by 3, etc., etc. A relation can be described by using a graph. So from this graph, I can tell that when x equals negative 2, the y value will be positive 5. Or when x equals 0, the y value will be negative 3. An equation would be another way of describing a relation. For example, y equals 2 over 3x minus 4. Or a relation can be described by using a set of ordered pairs. So this is an ordered pair, x and y. And a set of ordered pairs is made when many ordered pairs are put together. We usually place them inside brackets. And I'm going to use, as a matter of fact, the numbers from the table of values above to create a set of ordered pairs. So I'll write here 1 and 8. So these two numbers together, independent, dependent. That's one ordered pair. And then the next one, 2 and 5, 3 and 2. So we're going to say that the set of these ordered pairs will form a relation. Normally, when we do this, and you will talk more about it in grade 10, we use letters to name the relations. And we must use capital letters for relations and a semicolon after. And it is important that we enclose all these ordered pairs inside the braces. That's what these fancy curly brackets are called. Now, in this unit, we will focus on linear relations and analyzing them and putting them to work to solve various problems where linear relations are applicable. So to summarize what we just discussed on the first page, we're going to say that a relation is a description of how two variables are related. And in a linear relation, the graph will form a line. And that's where the word linear comes from. Now, most relations will involve an independent and a dependent variable. Normally, the independent variable is the variable whose values we have the freedom to choose. And it's usually placed in the left-hand column on the table of values or on the horizontal axis or x-axis on the graph. So as you can see here on this chart, the independent variable will always go in the first column, dependent in the second. The dependent variable goes on the right-hand column, so on the right-hand column, and or on the vertical axis, which is the y-axis on the graph. So if you looked at the table values, here's the independent and here's the dependent on the right. If we looked at the Cartesian plane, here is the independent, and this is where the dependent variable will go. And all the relationships are described of dependent versus the independent variable. Now, relationships that we are going to look into in this unit are categorized in two types: direct variations and partial variations. Now, what does a direct variation look like? I'm going to take a look at their equations, table values, and graphs to make sure we understand what they have in common and what they have different. Now, in a direct variation, the dependent variable varies, as the name says it, and you probably guessed it already, directly with the independent variable. Or in other words, we say that the dependent variable is a multiple of the independent variable. So as an example here, I would give y equals 4x. So the value of y varies directly on x or varies or depends only on x. And the variable y is a multiple, so 4 times the variable x. Now, in a partial variation, the dependent variable varies partially or indirectly with the independent variable. It is a multiple, so dependent variable is a multiple of the independent plus an initial or fixed amount. So I'm going to take as an example our direct variation, y equals 4x. So if you want to make this partial, you add a certain number or subtract a certain constant number. For example, number 2. So the variable y will depend on x, but it will also depend on how big or small this constant number is. So we say that the variable y will partially depend on x because it will also depend on this constant number. Now, if we looked at direct and partial variation in a table of values, this is what it looks like. In a direct variation, when the variable x is 0, the variable y will also be 0. So imagine this relation here. If x equals 0, then the value of y will be 4 times 0, so which will equal 0. So you can understand right away whether the relation is or describes a direct or partial variation by checking with what the values of y will be at x equals 0. So if this number is 0, it's a direct variation. Now, in a partial variation, however, as you probably might have guessed, when x equals 0, the value of y will be a certain number. So, for example, in the relation that we wrote in here using an equation, if x equals 0, the value of y would equal 4 times 0 plus 2. So the value of y would be 0 plus 2, or the value of y will be 2. So it won't be 0, but it will be a constant number. Now, graphically speaking, and this is my most favorite way of distinguishing the two relationships from each other, in a direct relationship or relation, the graph will start at 0, 0. Why? Because 0, 0 is a point on the graph, because the y-intercept is 0. And that's why the line will start exactly at the origin of the Cartesian plane at 0, 0. In a partial variation, however, the graph will intersect the y-axis at a certain value, and we call this the fixed value or the initial value. Now, as for the equation, as we discussed, the equation in a direct variation will be simply y equals mx. So the y-intercept will be 0. And in a partial variation, the equation is y equals mx plus b, where b will be a number different than 0. Now we're going to take a look at some examples, and we'll have to answer a few questions. So we're starting with easy questions. Identify the independent variable in each set of variables, so independent and dependent. So the number of guests at a wedding reception and the cost. So which one do you think is independent and which one is dependent? So I'm thinking that the cost will depend on how many guests we have. The more guests, the higher the cost. So I will say that independent variable will be the number of guests, and the dependent variable will be the cost. Now, the weekly pay and the number of hours worked. So how much you get paid will depend on how many hours you put in. So that means that weekly pay depends on the number of hours. So the number of hours is independent, and the weekly pay will be the dependent variable. Let's move on to the next example. Example 2 is asking us to find the equation in the direct or partial relationship from a given graph. Now, if you look at this graph in here, you can tell right away that it is starting at a point where y-intercept is different than 0. So we are going to say that this is an example of a partial variation. Now, there is a lot of information given in this graph, and I'm going to start by the title, the heating of a chemical. So that means that this graph will describe the heating of a chemical, and more specifically, the relationship between the temperature and the time. So depending on the time that the chemical has been under heat, then we can see what the temperature of the chemical will become. So the initial amount, remember, will always be the y-intercept, which tells us that at time equals 0, the temperature of the chemical was about 25 degrees. So initial amount is 25 degrees. Don't forget unit measurements. The independent variable is the time in minutes. And the dependent variable is the temperature in degrees Celsius. Now, the rate of change. This is not something new. We have done rate of change plenty of time in the previous lessons. So for the rate of change, I usually like to pick two numbers. And I like to pick two numbers whose coordinates are easy to identify. So I'm choosing here to use the 2 points A and B. So these are the 2 points chosen. And I will allow myself to go from point A to point B. And I will make sure that I can only move vertically and horizontally, so no diagonally. So if I moved vertically from A to B, it means that I have to move 5 units up, and horizontally I have to move 2 units to the right. That tells me that the rate of change is 5/2. Now for the equation of this particular line, we're using the temperature. Depending on what you want to call the independent variable, in our case, I'm going to let this be represented by capital T, and I would let the time be represented by lowercase t. And I will show this on my graph as well, so that everyone can understand when reading my work, everyone can understand what the meaning of the equation will be. So we're going to say that dependent variable t equals the rate of change 5/2 multiplied by the independent variable lowercase t plus the y-intercept, which in our case is 25. Now, next we are going to take a look at the two tables of values, and we'll have to answer the following questions. The focus of this example is to find the equation of a direct or partial relationship from a given table of values. So we have this table of values. As you see here, we have certain values that are missing in here. So we will have to first take care of the missing values. So we have to complete the table. We're going to use our intuition here. These are linear relations. Okay, so that we know for sure. And I'm checking with the x values. As you can see here, the x values are changing by the same amount. So it only makes sense that the next number on the chart must be number 6. I'm going to change the color so that it kind of stands out here, because it looks pretty much the same. Here we go. And then I will look into the y values. So I see the y values are increased by 2. But I want to make sure, and I will check the rest of the y values, because it has to be a consistent pattern based on the first differences. So that means that after 7, we must have number 9 here. And if you can double check your pattern here, you see that all the numbers are consistently increasing by 2. So step number 1, check. Indicate the type of variation. So if I want to know what type of variation I have to search for the ordered pair where x equals 0. Now, take a look at the values of x in this chart. Do you see x equals 0 here? So we start at 1 and at 6, so there is no 0. Then I'm thinking, how can I find it? So if I don't have an unknown, I always think, how can I find it, right? So we never give up, and we always think of other more intuitive ways to discover and access information. So now I'm thinking, if I went 1 unit back, then I would have probably seen the 0. See, if I was given 1 row above my first one here, I would have seen 0. So I'm going to write 0 in here. And then I'm thinking, if x was 0, then the y values, since they are increased by 5, but they are increased by 2, so 5 to 7, 7 to 9, they are increased by 2. It means that the previous y value must have been 2 units less. So that means that it must have been 5 minus 2 or 3. So that tells me that when x equals 0, the value of y is 3. Would this be direct or partial? So remember, it's direct when they're both 0. It's partial when y is not 0. So we'll say that this is a partial relation because when x equals 0, y is different than 0, right? So it's 3. The last question is asking us to find an equation for this table of values. So remember that all equations will look like this. Y equals the rate of change or slope times x plus the y-intercept. Now your y-intercept is the y value at x equals 0, which in our case is 3. For the slope, we just go rise over run. So 7 minus 5 divided by 2 minus 1. And you can use any set of ordered pairs here. So in our case, it's 2 over 1. So we'll say that the equation of this particular relation described by this particular table of values is 2x plus 3. Now, if you would wish to, you can actually start with the next table of values on your own. As you can see here, there is more numbers missing. Don't be afraid of it. Just work on a problem one step at a time, like one portion at a time. For example, I would focus on filling in the x values. And I'm very happy to notice that there is only one x value missing, so that shouldn't be hard. As you can see in here, we go from 0 to 1, so most likely we're changing by 1 unit. Double check the rest of the x values, and it seems that all the x values are following the pattern consistently. So that tells me that the x value here must be 2. And then I would look into the y values. So for the y values, I have 2 empty spots. So I'm going to focus on what I have. You always focus on what you have to figure out what you need to know. So what I have is these 3 consecutive y values. That should be enough. So I see that 27 to 22 means that I'm going down by 5. 22 to 17, oh, I'm going down by 5 again. That means that most likely I should be going down by 5, which means that the next number must be 17 minus 5, which is 12. Now I will double check if this will create a consistent pattern with the next difference. So 12 minus 7 is also 5, so I am very happy about this. Now I need to fill only this little spot here. So remember, if the numbers are decreased by 5, it means that the number before 27 must have been 5 units bigger. And 27 plus 5 equals 32. So now we're going to say that we have filled the table of values all right. And we notice that when x equals 0, here y equals 32. So we'll say that since the y value is different than 0, then this makes a partial variation. Now the next thing we want to do is write the equation. Now the equation will be in the form y equals mx plus b. I always start from the formula, the basic formula, and then I think of the numbers I need to find or the numbers I need to put in. So the numbers you need to put in are m and b. So I need to think of how to figure them out. I need to know their meaning in order to figure out how to find them. And I always like to start off with b. It's so easy to identify it from the chart. Wherever x equals 0, that y value will give us b. For the slope, we can take any set of order pairs. I like the first 2 sets. So we'll have 27 minus 32 over 1 minus 0, which makes negative 5 over 1. So that means that the equation of this particular line is y equals negative 5 over 1x plus 32. So it's a partial relationship, and it's a decreasing line because the slope is negative.